Hello, my name is Maciej. I'm a high school student, and today I will talk about my project, the Drone Payload Release Mechanism, a device for dropping things. This presentation will consist of 6 parts. Background, where I'll tell you what the project does and its use cases. Requirements, where I'll give you some bullet points about what it needs to be able to handle. The receiver and the controller, where I'll individually explain the 2 most important parts of the project. Alternative modes, which I'll show you later, and code explanation, where I'll try to explain the code of the project. So first part, background. What is it? The drone payload release mechanism is a drone attachment that drops items from height. It is usually used to test track resistance, communication range, and parachutes of other small devices, such as small rockets, satellites, transceivers, and things like that. The drone payload release mechanism was created for a team at my high school who specializes in creating devices such as small rockets, parachutes, and satellites. Second part, requirements. What it needs to be able to do. There are two main parts of the drone payload release mechanism. The receiver, which is the main part that is attached to the drone and drops the payload, and the controller, which communicates with the receiver and controls it. The receiver must be able to lift up to 500 grams because that is usually the upper weight limit of most of the projects that are tested or created by the team. It has to be lightweight so we don't strain the drone and make it more or less controllable. And it has to be secure, which means we have to get the payload under control or the payload or the tested project. So we cannot drop it unless we want it to. The controller must be easy to use. It has to prevent accidental activation, so again, the payload doesn't release unless we want it to, and it has to have reliable connection to the receiver. Third part, the receiver. The receiver is the most important part of the drone payload release mechanism. It uses Esp-Now as its microcontroller, and it directly controls the release mechanism. It is attached to a drone, which enables it to fly and to drop our payload from various heights. We can also estimate its current height by using built-in barometric pressure sensor. It consists of 2 main parts, the power management circuit and the release mechanism. The power management circuit manages powering of the whole receiver. It consists of 3 main active parts, the battery charger module, the step-up boost converter, and the battery itself. It is a lithium polymer 3.7 volt battery. The battery charging module manages charging and discharging of the battery, as well as protecting it from overcharge, over discharge, and short circuits. And the step-up boost converter converts the voltage from 3.7 volts of most lithium polymer batteries to 5 volts. Now, we could technically convert the voltage to just 3.3 volts, which would be sufficient for the ESP32, but since we want to power components other than the ESP32 as well, we need to convert the voltage to 5 volts. The release mechanism is mainly made of 3D printed parts and a servo motor, and its main purpose is to carry and drop the payload. There are actually 2 versions or designs of the release mechanism, the slide ball design and the rotating hook design. The slide ball design is harder to manufacture, but can bear more weight, and the rotating hook design is easier to create but cannot bear as much weight because all of the load is applied to the axle of the servo, which can snap easily and break off. You can see the main support beam of the receiver is 3D printed from PETG, as well as the compartment for the electronics where most of the electronics beside the servo motor are mounted. You can also see there are 2 mounting holes on the two sides of the support beam, which are there so we can attach the receiver to the drone. Fourth part, the controller, the primary user interface. So the controller is the primary user interface to the receiver. It is also based on ESP32, and it communicates with the receiver wirelessly through Esp-Now protocol. It is powered through USB-C cable, which can be connected into any 5 volt power source, for example into a power bank. Its 2 main parts are the main circuit and the button board. The main circuit is the most important part of the controller. It contains all of the most essential parts, for example the ESP32, most of the wiring, and the OLED display, and it is built on a breadboard, which makes it easily modifiable. The breadboard is attached to a glove, from which it can be removed, because the breadboard is attached to the glove by using an elastic band, which is sewed to the glove on one side and held by metal pin on the other side. So if we remove the metal pin, we can slide the main circuit out of the glove. The reason the main circuit or the controller is built around the glove is I wanted to create a controller that is hard to lose, so you physically cannot lose it unless you remove the glove, and to make it non-intrusive, so when you wear it, it doesn't interfere with your other work. For example, when you're carrying something and you have the controller on, it should not impair your ability to carry something. On the other side of the controller, there is a button board, which is sewed to the palm side of the glove permanently, so it cannot be removed unless you undo the stitches. It contains 4 push buttons, 1 for each finger, and it is built on a custom edged PCB. It is connected to the main circuit with 5 wires, 4 wires for each of the buttons, and 1 extra wire which is connected to the 5-volt rail. You can see the button board is slightly skewed, and the reason for that is ergonomics, which makes it easier to press. I would also like to point out that in real life the button board is covered in this sort of padding, which makes it more comfortable to press, but I removed the padding on this picture so you can see the buttons themselves. The controller has a variety of possible interface elements. The two main interface elements are the button board on the back and the OLED on the front and the OLED display on the back. The additional possible interface elements are the gyroscope and accelerometer, which can tell if you tilt or move your hand, the flex sensor, which can tell how much you bend your fingers, and the buzzer, which can or an LED, which can notify the user once certain criteria are met, for example when the drone reaches certain height. The reason you cannot see the last 3 on these images, nor they are built on the real controller, is that there's simply no use for them in the drone payload release mechanism, so even though they are possible, they are not used. Last thing I would like to mention about the controller is its screen. It tells you 6 different kinds of information, one in 6 lines. So starting from the top left, first line is the reach indicator. It tells you if the receiver and the controller are in reach. We know that by sending a message through Esp-Now to the receiver and waiting for a response. If we receive a response, that means the receiver and the controller are in reach. If we don't receive a response, that means the receiver is either turned off or out of range. On the second line, you have the refresh timer. The refresh timer is kind of a loading bar that runs in a loop indefinitely. It tells us when the screen of the controller is refreshed. So even though the controller, the main CPU, runs at much higher frequency, we are limiting the frame rate of the OLED display of the screen, so quickly changing data are easier to read. The third line is callback frequency, which is one of few pieces of information sent to us by the receiver. It tells us the frequency at which data packets are sent. So if we have frequency 30 times per minute, that means we reach 1 packet of information each 2 seconds. It can be set on the receiver, which I'll show you later. I would like to mention that third line and second line are somewhat related, and one can affect the other. On the fourth line, you have pressure on the receiver, which is another piece of information we receive from the receiver. It's more precisely is the data that it receives from the barometric pressure sensor. And the fifth line is error line. This line displays all of the errors, either when they're from the controller, or when they're received from the receiver. So for example, if the barometric pressure sensor on the receiver, which is connected to the receiver through I2C, stops working or is not present, the receiver sends an error message to the controller, which displays it to the user. The last line is a vertical one, and it is on the right of the screen. It contains 4 characters, either underscores or hashtags, and these 4 characters represents 4 buttons on the button board. So each one of those characters represents one button if it's either its press state or unpressed state. We display the button states in this way, so if the button board breaks or malfunctions, we know it before, for example, we accidentally drop the payload. So you could say it's kind of a safety measure. Fifth part, alternative modes, secondary controlling modes. So what are they? Alternative modes alter workings of some part of the drone payload release mechanism, mainly its code. They are designed to aid in certain situations. They can be thought of as some kind of accessibility settings. There are 2 alternative modes, light sensor mode for the receiver and serial control mode for the controller. First, the light sensor mode. What is it? So, normally when we want to drop the payload, we have to send command from the controller to the receiver, and if the receiver receives it, it drops the payload. But when the receiver has light sensor mode activated, instead of waiting for a command from the controller, it drops the payload when it detects that the flashlight of the drone has been activated. It checks for that by having a photoresistor, which is an electrical part that changes its electrical resistance based on how much light hits it, and we have this part mounted next to the flashlight of the drone, which enables us to tell if it's been lit or not. The main advantage of this approach, of this alternative mode, is that it doesn't require the controller to exist, because we control both the drone and the flashlight of the drone, and thus the release mechanism, from the same exact remote, which also means they have the same exact range. Because in normal mode we sometimes can encounter a problem that the range of the Esp-Now can be slightly smaller than the range of the drone, which can lead to some issues. But this alternative mode requires additional electronics, mainly the photoresistor to detect the flashlight and some part to cover the photoresistor, so other light sources don't interrupt with our flashlight detection. It also requires the flashlight feature to be present on the drone, obviously. Although this flashlight feature nowadays isn't that rare, it also isn't very common in lower price range of the drones. Another small disadvantage is that we cannot receive any data from the receiver because there's nothing to receive them with if we don't have the controller. Also, the Esp-Now is not activated when light sensor mode is in use. So we cannot both have light sensor mode and Esp-Now activated. Second alternative mode is serial control mode. So, normally you use the controller by wearing it on your hand, pressing the buttons on the button board and reading output from the display. But if for some reason the user cannot use the controller normally, for example they have 2 big hands, they can use serial control mode by connecting their controller to a computer, and if this happens, the controller effectively becomes an interface between the serial monitor and the receiver. It works somewhat like a CMD program in Windows operating systems. We send commands by typing, and we receive our output by reading from the serial monitor. The main advantage of this approach is that people that cannot use the controller normally can use the controller. Another advantage is that it has a smaller chance of accidental activation, so because it's much more difficult to accidentally write a command than to accidentally press a button. And it also enables data logging, which means saving the data to our computer by just saving log from serial monitor, which enables us, for example, to calculate how much time we spent in the air or the speed of the drone. But it requires the controller to be connected to a device with serial monitor, which is usually either a computer or a notebook, which can be somewhat impractical to carry around in field. Sixth part, code explanation. Inner logic of the drone payload release mechanism. In this part, I will try to explain how the code of both the receiver and the controller works by using flowcharts, which should make it easy to understand. I would also like to point out that the flowcharts are somewhat simplified, and some information, for example delays, initializations, or some more complicated logic will not be displayed here and will only be explained by me verbally, or not at all. So let's start with the receiver. At the start, which means when we power the receiver, it checks if light sensor mode is activated. If it is, we go to the lower path, which will start in the light sensor mode, which will turn us into the loop of light sensor mode. If light sensor mode is not activated, we will enter the upper path, which will lead us to the normal mode loop. Let's start with the normal mode. So when light sensor mode is not activated, we will firstly try to initialize communication with the controller, which means we will send a message to it and wait for a callback from it or some kind of response. If we don't receive any response, after a while we'll wait and try again. We do this over and over until we receive a proper response from the controller. This means that the controller is up and running and we can enter the main loop and start waiting for any commands from it. So at the start of the loop, we firstly check if we received any commands from the receiver. If we received any commands from the receiver, we will check if we received command to change the frequency. If we did receive command to change the frequency, we will change the frequency by cycling through a list of preset frequencies, and after that, we will send data from the pressure sensor, current frequency to the controller. We send data from the pressure sensor and current frequency always at the end of the loop. And then after that, we go back to the start of the loop. So if we didn't receive command to change the frequency, but we received command to drop the payload, we will drop the payload, wait a while, reset the release mechanism, because when we drop the payload, we open the release mechanism, and when we reset the release mechanism, we close it back up. And after that, we will send data from the pressure sensor, our current frequency, and maybe a confirmation to the controller that we dropped the payload, and go back to the start of the loop. If we didn't receive command to drop the payload, and if we didn't receive any commands to drop anything or to change the frequency, we'll just send data from the pressure sensor and current frequency back to the controller and go back to the start of the loop. This loop runs forever, so it doesn't end unless you cut it from power, cut the ESP from power. This is fact for every loop I will be explaining, for every main loop. So let's go back to the start of the flowchart, and let's say this time the light sensor mode is activated. So if it is, it will lead us to the main loop of the light sensor mode. At the start of the loop, we check if flashlight of the drone is activated. If it isn't, we'll wait and check again. If it is, we will drop the payload, open the release mechanism, wait a while, reset the release mechanism, and after that we enter in this sort of loop. Now, if this loop wasn't there and the flashlight was on, the code would run indefinitely, so it would keep opening and closing the payload, the release mechanism, even though we turn the flashlight on just once. This loop, which checks if flashlight has been turned off and not letting us continue until has been turned off, prevents that. So when you turn the flashlight on, we will run through the loop once and then wait until the flashlight has been turned off again, until we can go back to the start of the loop. This is for the receiver. This is code of the receiver. Now let's head to the code of the controller, which is somewhat more complex. At the start, we also have to decide if we start in normal mode or controller's alternative mode, which this time is serial control mode. We decide by checking if serial monitor is connected. Let's say it isn't. If it isn't, we start in normal mode and enter the normal mode loop. At the start of the loop, we read button inputs from the button board. And after that, we will check if payload release button is held down. If it is, we will check if it has already been held down for 3 consecutive seconds. If it isn't, we'll go back to the start of the loop. If it was, we will send a command to release the payload and go back to the start of the loop. If payload release button is not held down, we will check if frequency change button is held down. If it is, we will send command to the receiver to change the frequency and go back to the start of the loop. If neither of these buttons are held down, we will check if we received any new data from the receiver. For example, new information from the barometric pressure sensor or something like that. If we did receive any new usable data, we will redraw the screen with our new data and go back to the start of the loop. If we didn't receive any new data, that means the receiver is either offline or we just didn't receive any data. In that case, we just go back to the start of the loop without doing anything. Now, let's go back to the start of the flowchart, and let's say the serial monitor is connected. If it is, that means we start in serial control mode, and enter the serial control mode loop. At the start of the loop, we'll check if we received any new commands from the serial monitor. They have to be new. If we received the payload release command, we will forward that command to the receiver. If we received command to change the frequency, we will forward that command to the receiver. If we didn't receive any command, we will check if we didn't receive any command from the serial monitor. These two commands are from the serial monitor from the user. Then we check if we received any new data from the receiver. So if the receiver has sent us any new information, for example, new information from the barometric pressure sensor. If we did receive any data from the barometric pressure sensor, we will format that data and print them out to the serial monitor for user to see, to view. If we didn't receive any command either from the serial monitor or from the receiver, we will just go back to the start of the loop without doing anything. This is the code of the controller. And this is about my presentation. I hope you enjoyed it, and thank you for watching.